My name is Franz Meyer here at the University of Alaska Fairbanks, and we have been working on a project for the last couple of years that's called HydroSAR. And the project has a lot of partners in it. As I mentioned earlier today, the names of the partners and the organizations that are contributing to the work that we'll show today are listed on this slide. So we have myself from the University of Alaska Fairbanks, then a team around Lori Schultz at the Marshall Space Flight Center, and a team around Batuan Osmanoglu at the Goddard Space Flight Center. And then, of course, we work very closely with ICIMOD in all our activities to make sure that the data sets and the tools are useful for you and available to you. The HydroSAR project had one main goal, which was to use the capabilities of modern SAR systems, which provide cloud penetration and allow you to sort of see the ground during flooding events like the monsoon event that's going on currently in the HKH, and extract as much information about floods we can from these data sets that we have available to us. Predominantly, the data set we work with is the so-called Sentinel-1 data set. These are data provided by the European Space Agency, and they observe most areas in the Hindukush Himalaya once every 6 to 8 days when we take ascending and descending geometries together. From these data sets, we have created a bunch of information layers. These first two data layers that you see here on the left-hand side, these are image time series. These are basically fully geocoded image time series and color-coded versions of those images that are very useful for you for visual analysis. The web service that we'll show you later today will contain some of these color-coded image products, these RGB composites. And those are useful because they show surface water usually as either dark black or dark blue feature in the image. So those bluish features are often unobstructed surface water. So those are good for visual analysis. Then we have some quantitative layers. The main one that we want to present to you today is a surface water extent layer. So this is a data set that maps open surface water that's available in the environment using Sentinel-1 images. The product we'll show you has a 30-meter resolution. So if you are familiar with optical data sets, optical remote sensing data sets, this one, for instance, Landsat is one of those typical optical images. This flood extent map that we'll show to you today has the same kind of resolution at about 30-meter range. So in addition to these information products, what HydroSAR also tried to do is to create these data sets as efficient as possible. We are creating these data sets all in a cloud-based environment, which allows us to create these data sets quickly over large spatial scales. So it allows us to monitor the entire Hindukush Himalaya region in sort of a low latency manner. So we can provide data sets to you within hours after data sets were acquired by the satellite. So we have two kinds of computational resources that we developed. One of them is the one that allows us to create images automatically over large scales. This is what you see on the left-hand side. We also will provide or have provided ICIMOD and some of the partners with a cloud-based platform that allows, for instance, ICIMOD or other people that are interested to develop additional tools, additional products that we may not have developed within the project directly. So it's a cloud-based platform that allows you to analyze data sets separately if you plan to do so, if you're interested in doing so. So the team is leveraging expertise from a number of different NASA centers. The University of Alaska Fairbanks, where I am located, we have expertise in creating products, automatic products from SAR data. We have expertise in cloud computing. We also can provide access to SAR data sets through the Alaska Satellite Facility, which is NASA's main data center for SAR data. And ASF is also located here in Fairbanks, Alaska. The Marshall Space Flight Center, represented by Lori Schultz today, has a lot of expertise in looking specifically at weather-related hazards with remote sensing data. They've been working on flood mapping and flood monitoring for many years. And they also have a lot of experience in education and training in this field and in creating aids, little visual aids that make it easier for end users to interpret the data sets we provide. The Goddard Space Flight Center has additional SAR expertise. In the future, we won't present that today, but in the future, we'll also have an additional product that is led by Batuhan Osmanoglu, and that product will allow you to also get an estimate of the flood depth or the water depth in flooded regions. And so this product will come in the future, and it's being developed by Batuhan Osmanoglu's team. And then we also have connections at JPL. The goal here is mostly to make sure that what we develop today is applicable for an upcoming radar mission that's called NISAR, that some of you may have heard about. This is a collaboration between India and the United States. It is a 2-frequency L-band and S-band radar that's going to be launched in 2023 and will provide additional global data sets that are relevant for the HKH. And so through Bruce Chapman, who is on the NISAR team, we make sure that our technology is compatible with the data sets that will come in the future. And then, of course, we have partners in the United States through the SERVIR program and our great partners at ICIMOD that are making sure that the services we provide are relevant for the region. Just a few words on the SAR dataset, why we are banking on SAR. As you may know and have heard today, SAR is a high-resolution imaging capacity that allows us to observe the ground in a 24/7 manner, independent of weather conditions and independent of night and day. So the radar signals that are being transmitted from these spaceborne sensors can penetrate through the atmosphere and can penetrate through clouds and give you this ability to monitor ongoing events like the current monsoon event continuously. So it's a very useful data source especially for monitoring of flooding. An additional reason why it's so useful for flooding is not only that it can penetrate through clouds, but also that, as you will see here in this animation in a second, water surfaces or exposed surface water looks very distinct in these SAR images, and we can apply automatic methods to detect the standing surface water fairly reliably and in a way that you can automate it over large spatial scales. So this sort of a little bit corny animation shows that a little bit. So the SAR system during flooding events, this radar signal can penetrate through the clouds and see the ground. You'll see that here in a second, how it sort of slices through the clouds in a very dramatic fashion. So let's see if that comes up. So we can see through those clouds and expose the ground underneath and monitor the ground underneath. And as you will see in the next part of the animation, this open surface water looks very dark, very different from the rest of the image, and that's sort of what we exploit to detect the surface water automatically. And then once you have the surface water detected, you can overlay that in a GIS system on things like roads or settlements to understand sort of the impact of an event. So here another one of these images to show you a little bit what modern radars can do. Systems like Sentinel and the upcoming NISAR mission provide regular observations every 6 to 12 days, depending on where you are on the globe, and allow you to track an ongoing event over time. So this is for the 2020 event, for instance, this time series here on the right-hand side. You see these dark spots developing, hopefully. And so these are indicating open surface water, and you can sort of monitor that surface water over time. A little bit of a word, I mentioned the Alaska Satellite Facility. The reason why it is very useful for us to work with ASF is that the Alaska Satellite Facility is the NASA data center for SAR data, and it makes all free and open SAR data sets globally available to anybody that is interested. So we currently are making available the global Sentinel-1 archive, which is that sensor that I showed you on the previous slide. We have all these data sets available in the cloud, which makes it easy for us to develop resources that sit in the cloud and leverage this data set. And we also will host, ASF will host the NISAR data set. So this upcoming mission will also be hosted by ASF, which makes it easy for us to take NISAR data and send it through the same workflows that you will experience today. So just a word about how in very broad strokes, how the product is being created that you will be seeing today. So as I showed you earlier, the detection of surface water relies on the fact that surface water often looks much darker in the image than the surrounding environment. You see that here again in this example, these grayish landscapes here. This is regular, cultivated land. There's some sort of vegetation growing on this land. You see a little bit the topography in the area. Also, you have some agricultural fields, some urban settlements in this sort of brighter shades of gray that you can see here. The brightness on the land is caused by what's called diffuse scattering. So a sensor in space, sends out signals to the ground in a side-looking manner, in sort of an oblique angle. The signal travels to the ground, and when it hits regular land surfaces that have some sort of roughness and maybe vegetation growth on it, then some component of that signal will be sent back to the sensor. And how much signal gets sent back depends a little bit on the roughness of this environment and also on its moisture content. The higher the soil moisture, the brighter the ground, and the more vegetation, the more roughness there is, the brighter the response. And so you can sort of see these variations and these shades of gray in this image on the right. However, if the radar signal hits water surfaces, if you look sort of out at a lake, in most situations, water surfaces are very, very smooth. And this smooth surface causes this side-looking radar energy to be scattered away in a different direction. So the signal is scattered in this specular way away from the sensor, and very, very little energy comes back to the radar. And that's why these water bodies look distinctively differently than land surfaces and much darker than land. And so in essence, what we do is we developed an algorithm that can find an optimal threshold that distinguishes water pixels in the image that have, on average, a much darker brightness. Here in these image histograms, you can see on the x-axis the brightness of an image pixel, and on the y-axis you see it's basically a count how many pixels have a certain brightness. And see in this particular image, the water pixels have a brightness of about -15, -12 to -15 decibels, while the regular land pixels have a much higher brightness. And we can see sort of a minimum between sort of the water distribution and the land distribution that allows us to separate those two in an optimal way. What you see in these two examples is that there's always a difference between the water scattering and the land scattering, but where exactly that optimal threshold lies is different from one image to the next. So in this case, the best threshold would be about at -16, -17 dB, while in the other image it's closer to about -10 dB. And in essence, what our approach has implemented is a method that runs in 6 steps. And what it does is it tries to find automatically the optimal threshold for every image to distinguish between the water pixels and the land pixels for every scene. And so the threshold is going to be slightly different for every image. It's going to be adapted and automatically detected for each one of those images. The way this works is we take a stack of images, we geocode all of these images using a DEM. Once we have all of those geocoded, we are trying to find parts of the image where so we basically take the image and we tile it into smaller pieces. And then we try to find those smaller tiles that contain both land and water. Like this particular tile has about half land, half water, as you may see it here in this schematic sketch. And if we would look at the histogram for this particular tile, because it has both land and water in it, it would have two separate humps in that distribution. We have that darker component of the histogram for the water pixels and the brighter one for the land pixels, and we can find an optimal threshold. And what we do is we find the a few of the best tiles to estimate an optimal threshold for this particular scene. And then once we found the threshold, we can get an initial surface water map, like the one that's shown here. Blue is sort of an initial detection of surface water. This initial map may have some missing detections. It may also have some false detections in it initially. To remove many of these false detections, we do then some sort of post-processing that I'm not going to explain in detail. It basically uses, again, the DEM information and says things like if a water detection is far away from a nearest drainage system, so if you have a river here at a certain altitude and the water pixel is like 100 meters above that drainage system, it is very likely not flooded. So we do some make some assumptions like, okay, the pixel shouldn't be too high away from the nearest drainage. We look at the brightness of the pixel and some other criteria to throw away some pixels that are likely bad. Once we have our final water mask, we actually separate out permanent water from waters that are related to flooding. You will see that in the interface that Sudip will show you later. And then all the data sets are made available on a web platform in directly out of the cloud. And again, Sudip will show you that web platform in a little bit. So what this will look like is like this example here on the left-hand side. This is actually taken directly from the web platform for an area in Bangladesh. Sudip will provide you the link to the platform. The link is also here in the slide deck. So if you downloaded the slide deck, you can click on that link directly. What you will see in the platform is the permanent water in a slightly darker shade of blue. So the darker blue areas here are the permanent water. We created the permanent water layer using our SAR datasets. What we did here is we looked at SAR datasets for mid-March to mid-April, which is usually the time when the water extent is the lowest in the region, and then use that basically as an indication for the permanent water. So the blue one is the permanent water, and the lighter blue one is the inundation information related to the flooding. You'll also see that you can also visualize these color-coded SAR images that I talked about earlier, and we'll explain those a bit more when Lori talks about the quick guides for analyzing these data sets. So this is an area here again in northern Bangladesh, just to show you a little bit what that would look like. The data sets that are available in the platform can be animated as a time series. So Dip will show you that also. And you can see here how over time, for the 2021 event, how the surface water extent has increased over time. Before I hand you off to Lori, just a few words on how, what is good about this approach and what are the limitations. To show you to find out how well the approach is doing, we have compared the approach extensively using two different comparison methods. A first one that I show you here is a comparison to water extent maps from optical data. There are established ways how you can detect surface water in optical data sets using things like normalized difference water index and similar approaches. What I show you here is some data for the 2019 Missouri River event. where there was flooding along the Missouri River in the United States. So this is the area that we looked at. We looked at a part of Nebraska in the United States. You can see here the Missouri River coming down. For this event, we had available Sentinel-1 SAR images, but also Sentinel-2 optical multispectral data sets. And so this up here shows you a false color multispectral data set where in this sort of bluish color you can already see surface water extent. Missouri was a good example because there were a lot of cloud-free scenes for this particular event that we could utilize for comparison. And so what we do is we take the Sentinel-2 data set and the optical data set, and we apply these standard approaches like the modified normalized difference water index approach to highlight the surface water. Here the surface water is shown in blue. And then once we extracted the surface water from the optical data, we can compare that to the surface water detections in SAR. And we had a few events, a few data sets where we had the optical data and the SAR data set close by. This is one example where they were available at about the same time step. So on the left-hand side here, you see the SAR-based water extent. In the middle, you see the optical water extent. You can already visually see that they're very similar to each other. And on the right-hand side is the comparison. So overall, they are very, very similar. Detect overall a similar water extent with some few missing detections in the Sentinel-1 case. This is another example. Here we have an optical image that's about 4 days apart from the SAR image. And again, you can see that the Sentinel-2 and the Sentinel-1 water extents are very similar to each other. The ICIMOD has also done some initial analysis of the data quality using a similar approach. In this case, what ICIMOD had been doing is taking the SAR water extents that we provide and comparing them to Landsat data sets using, again, the normalized difference water index approach. And so here's one of those examples. What you see here on the right-hand side is in black. You see the Sentinel-1 water extent, and just underneath is the Landsat 8 water extent. And it's very difficult, I'm assuming, for you to see the difference here because they're very, very similar in overall extent, and they're all also very, very similar in terms of the number of water pixels that were found. So very comparable results here for a data set from this year. This is a separate data set. This is from last year, from 2020. In gray, here you see the HYDRO30, the SAR-based surface water extent. In blue, you see the Landsat-based surface water extent. They don't overlap a great deal in this case, but there's a part of the extent that is overlapping. And also here, the overlap region shows very comparable surface water extent results. A second way how we started evaluating the quality of the product, somebody earlier talked about some collaboration they're doing with Google. I think that was one of the participants from India. We are also working with the Google flood forecasts a little bit, their near-term flood forecast system. And what we've been doing is we try to compare our surface water extent to the forecasts provided by Google for the same days. Here we don't expect a perfect match, but we at least want to see that they are similar in extent. And so you see here in blue, in each case, you see the SAR-based surface water extent. And in the orange or red colors, you see the Google forecast. And I think overall, the match is between those two is very good. Similar for this case, which was from just a few days ago, July, the 22nd of July, for an area in Assam, India. Here, the forecasted extent is a little bit larger, but overall very comparable to the detections we found from SAR. So overall, we feel pretty good about the approach, but it doesn't mean that the approach doesn't have limitations. So first of all, I want to mention that what you will see today is really the first fully operational flood mapping approach from SAR that exists. There are several attempts that are going on in the by the European Space Agency and by NASA to provide similar services, but this is really the first time that we, develop this service and let it run completely unsupervised. So everything runs fully automatically. So there will be, and I hope you will point those out to you, there will be issues here and there, where data sets have characteristics that we didn't necessarily expect. And so sometimes there may be issues with the data set. Please have, first of all, patience with us. And if you see something funny, report that back to us so that we can, look at these data sets to make the service more robust. There are some known limitations. The two main ones that I want to highlight today is, so there's sometimes issues with wind roughening. I said earlier that water always looks very dark in SAR images, and that's true most of the time. However, if you have stronger winds, you can have the surface of the water will not be smooth anymore, and that wind roughening can cause some issues off and on in water detections. From what I looked at in the service that we provide for you, this is a very rare event. In most cases, I haven't seen any major issues with wind roughening in the data set, but it may occur on occasion. The approach that we developed is predominantly detecting open surface water, so standing surface water that you can see from space. Of course, when you have a flooding event, you will also have places where water occurs under forest covers. I'll show you an example here in a second. For instance, the mangrove forests in southern Bangladesh are a good example of that. There's definitely standing water under these trees, but the SAR data cannot penetrate these denser forest canopies deep enough, and so we won't be able to detect water under these trees. That is a similar issue that also you will have with a Landsat or a Sentinel-2 optical data set. So that is something to keep in mind. Another issue that I want to point out, and I will show an example for, is that we have sometimes the issue of mixed pixels, where a pixel contains not only standing water, but also land. So this can happen if the land is sort of undulating, if there's topography that's undulating. In this case, within a 30-meter pixel, you have puddles of water or little, pooled water, but you also have land surfaces. And so these pixels will appear somewhat darkened compared to what they look like before a flooding event, but they will not look, as dark as we would expect it for a completely inundated pixel. So we do lose water detections in places where we have mixed pixels, where there's both land and open water in a pixel. And I'll show you an example like that a little bit later. The last thing I want to point out is, so there was at least one person that mentioned that they have a very strong focus on urban mapping. SAR data sets or SAR sensors have this, the way they collect images is they look sideways to the ground, like shown here. And in urban settings, what this often means is that we don't necessarily see the water surface between the houses, because the house here causes an obstruction for a large area behind the house. And in many cases, this water body here is in a radar shadow and we can't see it. So radar overall has some problems and some limitations of detecting water in denser urban environments. So that's another thing to be aware of. Just a couple of quick examples of these limitations. I said we can't see water under vegetation. This you will recognize. This is the mangrove forests in southern Bangladesh. What you see here, this is directly taken from the platform that you will see. In dark blue, again, you have the permanent water. So you have all the rivers and some of the permanently flooded regions near those mangrove forests. In light blue, you have additional water extent that is related mostly to the monsoon flooding. And what you see here is the water detections end at the edge of this very dense mangrove forest. So we cannot see through that forest canopy and therefore cannot detect the water that is available under that forest canopy. So that's something to be aware of. In this case, currently the service uses Sentinel-1 data, which, if you're familiar with the different radar wavelengths, Sentinel-1 is a C-band radar. It has a wavelength of about 5 centimeters. This 5 centimeter wavelength cannot penetrate through that mangrove forest, and we cannot detect the water. The future NISAR radar will operate at so-called L-band. And L-band has a much longer wavelength of about 25 centimeters. And L-band has often the ability to penetrate through these mangrove forests. But what you would see in flooded cases, when the mangrove forest is flooded, instead of looking dark, you would see a brightening signal, like shown here on the right-hand side. So that's something that we can add in the future once NISAR is around, to also detect these areas that get very bright. The brightening comes here from the fact that when you penetrate into the forest, the radar signal bounces off of the water surface under the forest, then bounces forward, mostly against, say, a tree stem or some forest structure, and then gets scattered back very effectively to the radar. So in places where there's this water surface under the trees, we get a very strong response, and we get these very bright features. So this is, in this case, this is an example from the Amazon rainforest. The top tile shows you the rainforest during the dry conditions where there's no flooding, and sort of this grayish landscape here is the Amazon rainforest. The black component is a river going through the rainforest. The bottom tile shows you the same scene, but later in the season, in the rainy season. What happened, this river has swollen, it has flooded this floodplain under the trees, and you see this very bright response in all places where the trees are flooded. So NISAR will have some ability to see water under these mangrove forests in other parts of Bangladesh, vegetated parts of Bangladesh, that the C-band radar that we currently are using cannot see. One last example, let's see, what else do I have? Oh, so here's this example of mixed pixels that sometimes prevent us from detecting surface water. Maybe what I want to most point out here, on the right-hand side, you see water detections in blue on top of a radar image. You see a few things here. You see that most of the river is nicely detected. But you see also here, if you see my mouse, this here is also a river. This river was not detected because this river is fairly narrow. And you may see that the gray value along this river is darker, but it's not black. And that is because there's overhanging vegetation, and each pixel on this river has both some vegetation and some water in it. So you may see early on in the monsoon response that there are some of the narrower rivers that are not right away detected. As sort of you go through the time series and more rain falls and the river widens, many of these rivers become visible in the water detections later on as the rivers become wider. So at the 30-meter resolution that the product is provided in, for some of the narrow rivers, you may miss detections. Other misdetections are more easy to explain. This linear feature that goes across the river here, that's a bridge. So the bridge is obstructing the river in this case, and we cannot detect the water under that bridge. So we get a little bit of a gap in that particular case. And the last thing that I want to point out, Sometimes you may see issues with the data set in cases where we have bad data. So SAR is a very stable instrument overall, but sometimes even the SAR data sets have some issues. In this particular case, what I show you is a calibration issue where the instrument is not perfectly calibrated in some parts of the scene. You may not see that right away, but if you look at that river very carefully, you see that the river is very dark where my mouse is located, but there's suddenly a linear break. Can you see that? Where the river suddenly is much brighter. And then it's much brighter here, and then there's a line here where the river again turns dark. I hope you can see that somewhat. I'm highlighting that a bit more with these lines. And so Sentinel-1 is acquired in what's called individual bursts. So the image is actually put together out of many smaller images. And in this case, that particular part of the image was not calibrated correctly. And in those data sets that you will be seeing, you get the RGB images. What you see in the color-coded images is that the river looks blue up here, and then in places where the data set is not correctly calibrated, the river suddenly changes color and it looks red. And I hope you can see that here. And in that area where the miscalibration happens, the water extent product often has some misdetections. We try our best to detect surface water also in these places where calibration errors happen. Depending on how large the calibration issue is, we may miss detections in that area. And you can see here that there's a linear break where we have water detections down here in this case. Then there's a gap where the data is not correctly calibrated, and then the water detections show up again on the other side. So this doesn't happen very often, but you may see that off and on. And when you see it, hopefully these slides remind you what the source of this issue may be. And I think I stop here.